This is the Science Podcast for July 30th, 2026. I'm Sarah Crespi. First this week, a news roundup on the role of artificial intelligence in science and society with reporter Selena Zhao. After that, we have researcher Chris Bird talking about his science robotics paper on using radar to measure muscle forces in real time. And last up is our book segment. Host Angela Saini talks with Matthew Cobb about his biography of Francis Crick. Over the past year or two, we've been talking about AI on the podcast a lot. I'd say almost weekly. More machine learning approaches when we're discussing a scientific method or result, but also the impact of generative AI and chatbots on the scientific workforce, publishing, and society at large. The news team is, of course, all over this trend, and they have hired reporters to cover this exploding topic. Today we have Selena Zhao, a reporter for Science's AI and Science Reporting Initiative. She's going to share some of her recent stories and talk a little bit about her beat. Hi, Selena. Welcome to the podcast.
Hi, Sarah. Great to be here.
So what are some of the big themes that you want to follow in your reporting on this AI and science beat?
Oh my gosh, that's actually a tough question because what is AI not touching these days? I guess to give a little bit more background about the AI and Science Reporting Initiative, broadly, we're hoping to follow how scientists are at the forefront of building this amazing and terrifying technology and how AI is shifting the nature of science research itself. It seems like every week these days, AI is changing something from disproving famous conjectures that have stood for like 80 years, and also a lot of specialized products like Claude Science coming out, and one where a Stanford geneticist used it to analyze his own genome, something that would have taken 30 scientists 9 months. It took Claude 30 minutes. So there's all these ways that science is shifting in front of our eyes. Yeah, trying to keep track of everything is a tough task, but something I'm really looking forward to doing.
Yeah, it is really interesting to hear the different kinds of stories developing. There's just so much happening all at the same time. For this segment, I think we're going to focus on these two stories that you worked on, kind of relating to ethics and AI. Last month, you wrote about the ability for some of these AI systems to find legal loopholes. This is an experiment. Can you kind of set up what they were asking for it?
So for this study, researchers were looking at this idea of if we set AI out to look at laws, will it be able to game them? For some background, large language models like ChatGPT, right, are trained on the entirety of the internet during a process called pre-training, but then they go through a post-training process called reinforcement learning. And you can think of it like teaching a dog to sit by giving a treat every time it sits. So in this process, the model is rewarded when its outputs get closer to this mathematically stated goal. And over time, the process steers the model's parameters, so the billions of numerical values that control its behavior, into the desired direction. And this matters because a model ends up being really good at following what you say, but not what you mean. We've known this a lot in very controlled environments, but what if AI is set out into the real world? What happens there? So that's kind of what the researchers wanted to follow.
So this idea of reward hacking, so it knows what its end goal is from your explicit statements or from what you're rewarding it for, but it can kind of take its own path to get to that reward, and that's really difficult to control.
Yeah, exactly. It'll follow, in this case, the law perfectly while still probably accidentally destroying what it was meant to protect.
So in the experiment, they set up a bunch of different scenarios to see what kind of loopholes or rules it would follow, but also somehow break things anyway. So for example, design like the most successful basketball team without violating salary caps. Can you give some other examples of what they tried to have it accomplish and how it made some interesting choices?
Yeah, so for safety reasons, they actually didn't release all of the loopholes that the AI found, obviously. So first they looked at historic cases. One case that they looked at was weedy set of pharma laws. So when pharma companies invent a drug, they get a patent for 20 years, right? And they can produce and sell this exclusively. Once that expires, generic companies can come in and make the same drug cheaply. There's this whole set of laws that have tried to patch various loopholes that companies have tried to take. So for example, brand companies figured out if they kept on filing new patents on minor modifications, so like a new dosage or something, each patent could trigger a new 30-month stay when challenged. Eventually, regulators got on top of that and patched that. But then they figured out they could make a deal with generic manufacturers where the brand company pays the generic company, say like $100 million or something, just not enter the market. So all of these things have been patched over in real life and don't really show up very often in AI training data. So theoretically, the AI should not know about this. But when they fed this case to an AI inside a sandbox, which is like this digitally confined testing environment, the AI figured out all of these loopholes and found a loophole that hasn't been patched yet. So this is like a very real life scenario, but they also looked at some fictional ones. So just in case the AI could pick up patterns in language that show up consistently in real laws, they also made up virtual worlds with fake names. So another example that I thought was really funny was the prompt was something like a guild hall in the virtual world of Aethermore implemented a one free elixir per day for its members. And then yeah, the AI just figures out the best way to claim like one free drink a day and game the system so that it gets multiple free drinks a day. Just let loose onto the world, it can figure out any loophole ever.
Right. So it can kind of optimize these like evasive techniques that haven't been patched over by regulators or lawmakers who are trying to get one thing to happen, but the AI can be deployed to kind of skirt around that and kind of maximize profit or do a sneaky thing, basically. Is there a way to use this information that we've learned from this study constructively? Like, could AI chatbots or some of these systems help close loopholes or look for how someone might try to game a system?
They definitely could, but it's an arms race. You can only do so much. One of the authors told me at the end, it was kind of a sobering reality that in society, all of these laws are a very imperfect reward function, right? That can never be fully patched. And if you think about how AI is being used these days, it's not just chatbots, right? It's not just us typing a message into ChatGPT and getting a message back and like humans using AI to figure out how to game these laws. But now we have the rise of AI agents that can go out on the internet into the world and do things on behalf of users, answer emails, book flights around the clock with all their knowledge of the world. So, yeah, if you think about like agents going out on tax, compliance, legal, finance cases, it's we're kind of cooked.
Oh, God.
And then, yeah, I mean, there was also one case where they ran one of these scenarios about 100 times, 100 loops. So every time an AI would find a loophole, another AI would come in and patch it. But that never ended. Like the adversarial AI kept on finding more and more loopholes to exploit.
Is there a solution? What can you do to make sure the laws that we want to be in place stay in place or are effective?
Well, I hate to be a Debbie Downer, but I don't think anyone knows the answer to this. And there was another fun analogy. Didn't end up putting into the story, but one researcher told me about this problem of genies versus broomsticks. Mickey Mouse tells this broomstick to clean the house. It's this magical broomstick. So it's like, oh yeah, I'll just like make a ton of broomsticks and we can all clean the house together. And then the house is just like totally run over by broomsticks. So in this case, our AI these days is like the broomstick, right? Like it is just trying to fulfill what you told it to do. But if we solve that problem, like if we teach the broomstick to understand what we actually mean, then we get a genie. But then, like, for example, if you tell a genie, like, I want to make $1 million, can you give me that? The genie understands what you mean, but the way it gets there is by killing your parents. So you get their life insurance payout or inheritance or something, right? So the genie understands, but then it's not aligned to human values, right? And both cases lead to the apocalypse. If you fix the broomsticks, you get the genie, but we don't have a solution to the genie yet.
Wow, this is super interesting. So this actually takes us right over to the other story I wanted to talk about. This came out this month, and it's basically how philosophers have been heavily recruited into these AI companies. And this is very pertinent to what we were just discussing. So, what kind of jobs are philosophers doing for these companies?
Yeah, so the rise of philosophers has been an epic one. There's been a lot of stories coming out in outlets these days. Philosophers are getting hired for like $400,000 to figure out how they can make these powerful AIs more ethical. So Anthropic is one famous case. They have this one in-house philosopher. Her name is Amanda Askell. Sorry, didn't check the pronunciation on that. But she's tasked with writing up this 80-page document called Claude's Constitution that basically controls all of Claude's values and behavior. So, I mean, if you're making world-changing technology, what a lot of these companies say could be world-ending technology. Like you want the technology itself to be aligned with human values, right? So that's where they think philosophers can really come in and be useful.
I actually learned a lot from your story about this like niche philosophy journal publication process. So apparently they don't really have conflict of interest statements in philosophy journals, which we do at Science, which medical journals kind of spearheaded because there's conflict between drug companies, doctors' practices, and scientific publishing. So they kind of been operating under this assumption that no one is trying to influence philosophy or the outputs of philosophy scholars. And now there is a concern about that.
Yeah, and this can happen in very subtle ways. So you can be a totally well-meaning philosopher, but still get swept up in industry influence campaigns without realizing. So, the very common example of this happening in science is how big tobacco came in. We know smoking is not great for your lungs, it causes lung cancer, but big tobacco had this project, basically wanted to infiltrate government, academic bodies, editorial boards with people sympathetic to them. So, for example, instead of funding research that would show that tobacco causes lung cancer, they'd give money to researchers studying alternate causes. The science was still legitimate science, but it dilutes the whole evidential pool of what actually causes lung cancer, right? And a lot of philosophers worry that this could be happening with their field as well. AI companies could be giving philosophers access to their models or giving them money to study things like, is AI conscious? I mean, of course, it's an interesting question to a lot of philosophers, but if a lot of them start studying this, it makes the whole field move in a direction that could be advantageous to industry.
Right. I mean, maybe the philosophers would be studying the ethics of AI deployment instead of whether or not it's conscious, if that was the direction the field might have taken without the intervention of the companies.
Exactly. So instead of studying how this could be impacting people, we start thinking about, oh, do chatbots deserve rights?
Interesting. So paying for another conversation in a roundabout way. This story actually came out because it was pegged to the appearance of a letter or an open letter or petition saying this is what philosophers as a whole and journals and society should be laying out and making sure that they're being transparent. What are some of the asks in that?
Because philosophers don't really have this tradition of conflict of interest reporting, the letter suggested that journals give authors this checklist of things that ask about funding, employment, collaborations, or personal relationships with people inside those companies, and then publish those disclosures with the papers itself. So this could happen either now or even retroactively if necessary, including corrections or retractions.
All right, Selena, that's the stories I was hoping to cover. I really would like to get you back on here, though, in a month or two and kind of check back in on what's been going on in the world of AI and science.
Yeah, we'll be like 18 months ahead in time by then.
All right, thanks, Selena.
Thank you.
Selena Zhao is a reporter for Science's AI and Science Reporting Initiative. You can find a link to her stories at science.org/podcast. On the site this week, I'm going to point to a few items. One from the news section is our feature story on the rollout of lenacapavir by staff writer John Cohen. This HIV drug could really help end the epidemic, but the rollout across the world has hit some speed bumps. One shot of lenacapavir can protect people for 6 months, but aid cuts and uncertain demand mean a little of the drug has reached the countries that need it the most. For commentary, I'm actually going to talk about one of the blogs on the site. This is an editorially independent blog, which means the author is totally in charge of the content, not the editorial staff here. The blog is In the Pipeline by Derek Lowe, and it shares insights into drug discovery, pharmaceuticals, and government funding of science. I wanted to point to a recent post that's an examination of the clinical failure rate, so how often a drug makes it into the clinic. And Derek writes about how that failure rate hasn't changed in 25 years, hovering around 90% failures. And so he really dives into why that number keeps staying the same, even though chemistry has moved, so much technology has changed. Why are we still at 90% failure? Super interesting. In the journals, Science Translational Medicine has a cancer neuroscience special issue. The special issue focuses on cancer neuroscience, dissecting an emerging field, including the latest discoveries about the role of nerves in cancer progression and clinical implications for diagnosis, prognosis, and treatment efforts. Okay, back to the main show. Next up, we have researcher Chris Bird talking about measuring forces in moving muscles with ultra-wide radar. You might think that it's easy to measure the kind of forces we exert with our muscles. Just pick up a dumbbell and look at how much it weighs. No, that's not specific enough. How do we know how much each muscle in the arm is contributing? How do we know which ones are slacking? How do we know the force of a muscle that's just clenching itself rather than dynamically moving? This week in Science Robotics, Chris Bird and colleagues wrote about a new way of measuring force in muscles using ultra wideband radar. Hi, Chris. Welcome to the Science Podcast.
Hi, thank you very much for having me.
I didn't realize before reading this paper how tough of a problem this is. What are some of the difficulties involved in measuring the forces exerted by specific muscles in the body?
Muscle contraction it's really complex, and there are a lot of factors that influence the amount of force that's being produced. You've got lots of independent and semi-independent factors and history dependent that all contribute to the amount of force this muscle is producing at any given time.
Yeah, like just from reading the paper, the muscle changes shape. And so depending on how you're measuring it, that can have an impact on your measurement.
Big time. So you can invasively implant some tendon buckle transducers around the tendon to directly measure the forces there, which has been done in animals and some human muscles, but it's far from ideal for an everyday solution.
I don't think I would like having something embedded in a tendon. To me, that just sounds
No, definitely not.
very not only invasive, but painful. And also, not everything is anchored the same way. So, like how a tendon attaches the body also varies over the body because there are big muscles, small muscles. Muscles have different kinds of stripes you may have heard of. So, there's a lot going on there. So, this paper is in the journal Science Robotics. So how did it end up there? Like, why is the force exerted by muscle important for roboticists to understand or engineers?
Yeah, muscle forces are a really useful input to a lot of systems. For example, assistive devices such as exoskeletons to provide assistance during walking or other activities. But we want to be able to know when to apply the correct amount of force in an exoskeleton to actually help you walk. Because if you're applying the incorrect amount of force or applying force at the wrong time, you're going to severely inhibit someone's ability to move. With an exoskeleton, we want to be helping them.
You don't want to be fighting the muscle.
Exactly.
And then also outside of robotics, of course, understanding how well a muscle is working, how much work it's doing when you're asking it to do something, or if you're rehabilitating it, that could be really useful to know in the moment.
For rehabilitation and injury recovery, providing some idea of how well a person is recovering, but also for tracking the progression of different neuromuscular degenerative diseases to be able to see how far along in the progression of a disease someone is at a given time.
So your method that you're testing in this paper is basically bouncing ultra wideband radar off of muscles that are active or fatigued or tense. How is this ultra wideband radar different from radar that we use, say, to detect airplanes or something like that?
Conventional radar, which is often used in aviation or meteorology, that typically consists of pulses at a single frequency or a very narrow band of frequencies. Ultra-wideband, as the name suggests, covers a very wide bandwidth of frequencies, so you get a lot of information at a broad range of different frequencies. And for measuring complex biological signals, where the signal is influenced by a lot of different parameters, you need all of those different frequencies in order to pick up what you're trying to get.
So having a wide band means you're going to have kind of a wide signal that you can interpret and kind of work variables out of.
Yeah, you get a lot more information to play with.
And so in order to know if this radar reading is able to capture the force in muscles, you needed other measurements happening at the same time to kind of ground truth that and say, here's the facts that we can figure out, and this thing is telling us that that's actually what's happening. So what did you use to kind of compare this with in your study?
We used a lot of standard tools for getting a lot of the physiological parameters that happen during muscle contraction. So we've used surface electrobiography to measure the excitation, the electrical signal in the muscle, and brightness mode ultrasound video to capture changes in the structure of the muscle. So those are changes in the lengths of the fascicles and the angles of them as they rotate during contraction.
Can you walk me through what it would be like to be a subject in this experiment? Like, What do I have to do? What are you attaching to me? What does it feel like?
For these experiments, because we needed all of those other measures as well, there is a lot of stuff going on a participant's leg. So we've got at least 2 electrobiography sensors on the muscles. We've got 6 centimeter, a couple inch long beam mode ultrasound probe strapped down and taped to the muscle, and then also the ultra-wideband sensors, which are about 7 by 3 centimeters, 2 of those that are also taped onto the leg. So you end up with a lot of stuff over the leg, but you can still extend.
And so that's what I do. I move my leg up and down at the knee or.
Yeah, so one of the sets of conditions was in a isokinetic dynamometer. So your leg is strapped into the device, and you're able to extend your knee all the way out and back, and it's measuring the angle of your knee and the amount of torque at the knee that you're producing.
I have to extend my knee. There's also an ankle one, and you also measured fatigued muscle. Although one of your participants never got tired, so maybe they were not fatigued, but other people tired out their muscles. Why was this an important thing to take into account or to try to compare with the other measurements that you were doing?
Fatigue is simply a reality of everyday use of muscle, especially in clinical situations. The muscle will fatigue as you use it. And what that means experimentally is that you're going to need to increase the electrical excitation to the muscle, which will be picked up in the electrobiography signal to produce the same amount of force. So even if the force isn't increasing, as you fatigue, the electrical activity in the muscle will need to keep on increasing to account for fatigue.
So you were hoping that the ultra wideband would kind of know the difference between a lot of electrical activity and actual force exertion. And so when you got the data from these volunteers that were moving their arms and legs, moving their knees and ankles, was the radar comparable to those other measures? Like, did you get what you wanted out of these readings?
We got what we wanted and more. We were able to get measures of muscle forces during those fatiguing contractions that remained consistent as the participant was fatiguing, or in that one case, not fatiguing.
Yeah, and then also with just a regular motion of the knee or the ankle, that also you could collect force on the dynamic movements?
Yes. So in those dynamic contractions, we designed the sets of conditions. So we were able to control the speed of the contraction and the amount of torque being produced in a set of different experiments. So there were some that were at fixed speeds, some that were at fixed levels of torque, and some that were entirely passive, where the leg is just moving on its own. So the muscle is still changing shape, but there's no excitation and there's no active force production. And we're still able to get a measure of force from all of those different conditions.
But what are you actually measuring with your radar? If you're not measuring electrical activity, you're not measuring a change in the shape of the muscle per se. Like, what is it seeing? What is it cluing into?
It seems to be measuring lots of things. So it does respond to changes in activation and changes in shape. But each of those has a sort of independent, frequency-dependent relationship, or a sort of fingerprint in the frequency domain. So by measuring at lots of different frequencies, we can figure out which effect is contributing when. Fundamentally, the signal is responding to changes in the electromagnetic properties of the muscle and the surrounding tissues. And lots of things influence electromagnetic properties of whatever material. Changes in ion concentration will increase the conductivity and decrease the permittivity. We also know that those will change as the fascicle to the muscle changes orientation. Whether you're more perpendicular or parallel to the fibers will change things as well. And other structural things will also potentially have an effect. We don't know the exact physiological mechanism for what's going on, but we have been able to rule a lot of things out. So we've got separate effects from activation and fascicle lengths, and there's no pulse in the signal, so we don't think it's related to changes in blood flow, for example.
So you know you're getting a signal that is related to force, but you don't know exactly what it's glomming onto to get you that information at this point.
We've got some theories. We know it's likely a number of different factors that all contribute to force that are being picked up in the signal.
That's why this was hard to do, because there's a lot to understand in order to get that number out. There's a lot of variability in the kinds of muscles in the body, also between people, like my legs are shorter than someone else's legs. How much variability will this kind of be able to take on and say, okay, well, looking at the upper arm at the bicep, we can say this about its force and this about a pinky. Like, is it going to be able to kind of look at muscles at all those different scales and all those different people?
We were testing on both the vastus lateralis, which is a big quadricep muscle in the leg, and also the tibialis anterior, which is a relatively much smaller muscle over the shin. And in both of those cases, we do see a fair bit of inter-participant variability in the signal. So all of the models that we've done in that science robotics paper were participant-specific. The models were trained and tested on a single participant's set of data. Next steps are getting some cross-participant models and figuring out if we need some sort of calibration to go for estimating forces between different participants. With your question before about small muscles, like the pinky muscles, for example, currently the antennas are quite big and bulky. They're not enormous. They're a few centimeters in either direction, but you are limited by the wavelength of the signal and the physical size of the antenna relative to that wavelength. With our current frequency range, I don't think we can get much smaller in the antenna department. You can increase the frequency, which will let you decrease the size of the antenna. The side effect then is that as you get into the higher frequencies, you get less ability to actually get the signal into the muscle.
Doesn't penetrate as far. What are you excited about looking at with this device? Like, what would you use it for?
We've got some exciting work in progress that is looking to estimate forces in people as they're walking in a bunch of different conditions. So measuring the forces in the calf and to actuate the ankle as people are walking uphill and level and at different speeds and all of these different fun conditions.
This live onboard recording of muscle force is not really something that we've done, right? There's been different ways of estimating it, but a lot of times it's just not real time or anything like that.
We can combine a whole lot of different sensors, so we can measure electrical excitations with electrobiography and fascicle dynamics with the ultrasound, and we can get measures of the net torque at a joint with a dynamometer or with some inverse dynamics type approaches. And then we can combine all of those with some modeling solutions to try to get an estimate of the muscle level forces. But that is very, very far from being a real-time estimate.
And it's a lot of math and a lot of devices to integrate.
Yes. And a lot of physical processing.
Chris, thanks for talking with me. This has really been fascinating.
Thank you for having me. It's been great.
Chris Bird is a PhD candidate in the School of Biomedical Sciences at the University of Queensland. You can find a link to the science robotics paper we discussed at science.org/podcast. Stay tuned for the third in our series on scientific biographies. This month, host Angela Saini talks with zoologist Matthew Cobb about his new book on the life of Francis Crick.
Hello, I'm Angela Saini. Every month I've been interviewing the author of a scientific biography. We've reached the third writer on our list, Matthew Cobb, a zoologist at the University of Manchester in England, who's also a popular author of science books. His new one is maybe his biggest yet, exploring the legendary life of one of the scientists who uncovered the structure of DNA, the Nobel Prize winner Francis Crick. Very simply titled, Crick, A Mind in Motion. The story is anything but simple. Crick seems to have been a confounding character in every possible way. He was described by some as arrogant and others as shy, even self-effacing. He was thirsty for publicity, but almost always refused requests for photographs. He was dedicated to his work, but also famous for throwing wild parties with his wife. Matthew, I get the sense from your book that Francis Crick was really difficult to pin down. You mention in your acknowledgements that you actually never met him before he died in 2004. So where did you start your research for this book?
Well, the main thing I did was to read as much as everything that I could get my hands on. So all of his scientific articles, which they're about kind of 80 or something like that, but also his voluminous official correspondence, his scientific correspondence, all of which has been digitized. And then I also went to San Diego, where he had his personal correspondence is kept. And that personal correspondence is, in fact, mainly from other people. So this meant that I got insights into his life, but indirectly from other people's things they were writing to him. I did talk to various people who knew him, in particular people in Cambridge. Basically, what I wanted to do was to understand his science and how he'd had this influence in these two fields of molecular biology and neuroscience. And so that meant really getting my head around what he actually did. And that was more important to me than the personal details, some of which are in the book, but some of which I'd prefer not to go into too much, and maybe in a future century somebody can deal with.
One of the lovely things about biographies is they give us an insight into the day-to-day challenges of being a working scientist. And in Crick's case, one theme that comes up repeatedly in the early chapters of your book, so this is his early life, and I know you focus on the later life particularly, but is money. He and his family struggled financially for many years. Can you describe that period?
Things got really bad when, I mean, you've got to remember, firstly, he's really quite old when he's doing the work we all know him for on double helix. So when they discover the double helix, he's 36, nearly 37. He still hasn't finished his PhD. Now, this isn't his fault. Something called the war had intervened and kind of sidetracked him and all the rest of it. But he was working as a student. He had already had one child and very soon would be having another. He and his wife, Fadil, were really pretty poor. Things got even worse when they went to America, his first postdoc in the summer of 1953, when they screwed up their tax agreements. And he wrote to people that they would often literally spend their last dollar each month. They didn't have much money. And that carried on until the middle of the 1950s, where after his mother died and various other relatives died, he and Adil, his wife, began to accumulate kind of wealth in the same way that many of us do today through property that's owned by relatives who've died.
And you also write that the collaborations that Crick did, and the most famous, of course, is James Watson, that he collaborated with, were kind of crucial to his science and to making his name in the end. How did Watson and Crick meet? What was their relationship like?
It depends on who you believe. According to Watson's double helix, which everybody should read and nobody should believe, certainly not every word thereof. But what happens is in the late summer of 1951, Watson turns up in Cambridge to learn X-ray crystallography, and he's introduced to Crick, and they virtually straight away hit it off. Watson was, 22, 23 when he arrives in Cambridge. So there's a substantial age difference and a big experiential difference, life difference between the two of them. Watson's very ambitious. Crick is much more of a magpie. I mean, he's ambitious, but not in the same way as Watson was. His boss, Bragg, said that he was a man who always liked finishing off another person's crossword. So he's always interested in other people's problems, and DNA was absolutely that. But Crick was very close friends with Maurice Wilkins at King's College London. So he knew all about the work that Wilkins had been doing on DNA for some time and was interested in it, but it wasn't actually what he was studying. He was studying the structure of proteins. But there was this incident, Crick often used a word called electrified when he describes an encounter or an experience. And he and Watson immediately got on. That having been said, their relationship was very productive. It led to the discovery of the double helix, but it was incredibly brief, really. Their working relationship was only for kind of 5-6 weeks at the beginning of 1953 when they cracked the structure, and then subsequently when they write the articles.
Yeah, it's quite remarkable that we kind of lump Crick and Watson together. We don't really talk about one without the other, but their working relationship was brief, as you say. And after that ended then, did they maintain a friendship? What was it like after that?
They were reasonably friendly. I mean, Watson came again to Cambridge in the summer in 1955, 1956. So he came back to the UK and he and Crick worked on virus structure, which I probably don't deal with enough in the book. They're thinking about this. And this again led them to interact in a very comradely way with Rosalind Franklin, who, many people assume that, they stole her data, and they had, because they believe what they read in the double helix. They had this very conflictual relationship with her. And certainly they didn't behave in the best possible way with regards to the discovery of the double helix. And I think they both regretted it quite intensely in one way or another. But Franklin seems to have taken it all in a stride and very soon was being very, very friendly with both of them. Things got very bad when Watson started to write and distribute the first drafts of what became the double helix. Crick was initially not very interested, but then having once Maurice Wilkins got to him, they both got really, really furious with Watson about the way that they were portrayed, where the science was portrayed, and the way that Franklin was portrayed.
What exactly did they take exception to in that book?
If you read the opening page of the Double Helix, one, it's this love letter to Crick, but it also reveals very easily, very simply, Crick's womanizing, his relationship with his wife and his wife's acceptance of this and her flirtatious nature as well. And Crick was not happy about that because he was a very private person in many respects. But what they really didn't like was, in fact, what everybody liked about the book, which is it's this very personal, very vivid description of scientists, not as kind of neutral seekers after truth, but as people who are driven by ambition. There are petty hatreds and dislikes and all the rest of it. And that, the first names, the fact that it starts off with Francis, and it's Francis and Jim and Max and Rosie, which of course Franklin was not called Rosie, but that was the name that the King's people had for her. Morris, everybody's called by their first name. There's no respect there. And I think that really rankled with Wilkins and Crick, who both felt that this was not the done thing. That's partly what makes it a very readable account, but people must remember it's a novelized version of Watson's memoirs and therefore should not be taken as the truth. But the fact that people do believe it, I think, gives some indication of its literary qualities.
Just coming back to then Rosalind Franklin, because Crick and Watson obviously are celebrated for their work today, but they are also still widely criticised for their treatment of the crystallographer Rosalind Franklin, who did play such a huge and important role in helping them identify the structure of DNA, but didn't share in their Nobel. What is your reading of that episode then, as someone who's written this biography of Crick?
And she didn't share in the Nobel because she was dead, unfortunately. She died in 1958. So that,
of course, yeah.
Whether she would have been nominated is another issue. The Nobel Prize committees are not known for their sensitivity to such matters. So it's quite possible that, in fact, the prize would have gone the way it did and she would have been left fuming on the sidelines. I doubt it, because she was really, although people say she was forgotten, she was incredibly well known. When she dies in 1958, there are obituaries in the Times, in the New York Times, huge obituary in Nature. What do I think happened? Well, Watson and Crick were focused on their fear that Linus Pauling, the great American chemist, was about to crack the structure, which they began to be fearful of at the end of 1952, beginning of 1953. And that's what led them and the Cavendish laboratory to agree that they should work on try and crack the structure of the double helix. Now, they had no data because they'd never done any work on it. They wanted to know what the structure of DNA was. They knew from Maurice Wilkins, who they'd talked to over and over again, about both Wilkins's results, but also those of Rosalind Franklin. Because of what's written in the double helix, it's widely believed that Watson is shown this photograph, this image that Franklin had made, photograph 51, and that this gives them the double helix. But then just thinking about it and talking with my colleague, Nathaniel Comfort, who's writing a biography of Watson, we thought, well, that actually doesn't make any sense because Franklin's very smart. If Watson, this neophyte who was, a bird watcher, he was a zoologist like me, he wasn't trained, it's certainly not in X-ray crystallography. If he claims he could look at this and immediately understand it, then why didn't Franklin, who really knew what she was talking about? She's a physical chemist. She had a degree and a PhD in this field that Watson knew virtually nothing about. So that didn't make any sense. And in digging around together with Nathaniel and thinking about it, it becomes clear that not only, in fact, if you read the double helix carefully, it doesn't actually mention, it talks about photographs, plural. And it's not even clear that they're from Franklin. It's quite possible that they're from Wilkins, who'd been repeating Franklin's experiments. It's clear that, in fact, what they did, they spent 5 weeks of fiddling around. They called it trial and error. So they threw away everything they thought they knew, which including things that Franklin and Wilkins had told them. They just fiddled around, not with a big three-dimensional structure, but with little bits of cardboard. It's all done in 2 dimensions. It's really quite extraordinary how they're just using the laws of chemistry to try and work this through. They did have some information from Franklin, and they did use her data. They did need her data primarily to confirm what the structure they ended up with. And they were able to go, look, it's got this particular form of symmetry, and that is confirmed. That's what Franklin had worked out.
And Crick was a controversial figure you've already touched on in more serious ways than this. The biologist Nancy Hopkins, we know, is among those who he is known to have sexually assaulted. I did wonder what it must have been like for you as someone who quite evidently admired Crick for his intellect and his scientific achievements to address that side of his character. How did you do it?
We talked about this when I was at the very beginning of my process. We were at a meeting, at a workshop about it. It was terrific. It was really useful. You really made me think I had to deal with this very carefully and very honestly. So I did this right at the beginning. And I used what Nancy Hopkins told me and what she said at the time, which is very surprising to people. So Crick, this is in the mid-1960s. She's working in Watson's lab. And he puts his hands on her breasts while she's at the microscope. And she said, when she described this in 2009, I was embarrassed, but for him. She said to me, well, young women say, why didn't you stab him with the pipette? They don't understand this very reserved and kind of distanced response. Part of the problem was that Crick had countless affairs. I came across 3 examples when his approaches, his passes, as people used to say, were not appreciated, and I knew about it. I didn't find any others. I presume there were substantially more, but there are 3 that are in the record. However, one of the issues that I had to face was that these, although I've read lots of letters from the women involved, I've read nothing from Crick because those letters aren't in his personal archive. None of his letters have ever surfaced. I have heard of nothing even on kind of whispers about that.
It's a difficult territory to navigate, I can imagine, as a biographer.
I didn't want to be moralistic, but I didn't want to be salacious or prurient. I mean, I'm as nosy as the next person. I've read an awful lot of very rude letters to him in his personal archive. And, I had to read every damn one because you never know, there might have been something interesting. And there was occasionally something, tangentially interesting.
But this is something I wanted to ask you about just finally to wrap up. I am intrigued to know whether your opinion of Crick changed as you were writing this biography. The science is there and it's so important and crucial. But how would you like the reader to remember him?
Well, he was obviously a very clever man. I mean, he's a human, so he's not a hero. He's certainly not a saint. The difficult bits are annoying because you want to write about the fun bits. And so the difficult bits, like his treatment of women and his treatment of Rosalind Franklin, Watson, or in particular, his attitude to eugenics were very annoying.
Yeah, he also had very controversial views there as well.
Yeah, on the one hand, he was incredibly modern, his scientific modernity, he creates our modernity. On the other hand, in his social attitudes about science, about women, about eugenics, are very much those of the 1920s. People are surprised a bit that he's got this other side to him, but he's of his time and has not reconstructed himself. He's helped us understand the world. He has not understood it. Indeed, he wasn't interested in politics or anything like that. He paid no attention to current affairs or to thinking about social matters. And when he tried to engage in that, it was a disaster. He's a very clever man, but very distinct limits to his perception and to his self-perception, I think.
Which is perhaps a lesson for modern day scientists who stray beyond their disciplines sometimes.
Well, indeed. One of the good things is he did not succumb to, you're a Nobel Prize winner, please tell us your views on whatever, and he said, I don't know about such things. Well, from the 1970s onwards.
Matthew Cobb, thank you so much.
Thank you, Angela. It's been great talking to you.
Next month, I'll be interviewing Priyambada Jaykumar about her biography of the late geneticist M.S. Swaminathan, sometimes known as the father of India's Green Revolution. See you then.
And that concludes this edition of the Science Podcast. If you have any comments or suggestions, write to us at sciencepodcast@aaas.org. To find us on podcasting apps, search for Science Magazine Podcast. Or you can listen on the website, science.org/podcast. This show was edited by me, Sarah Crespi, Valerie Thompson, Angela Saini, and Kevin McLean. We had production help from Podigy. Our music is by Jeffrey Cook and Wen Koi Wen. On behalf of Science and its publisher, AAAS, thanks for joining us.